to say hi. Oh.
Hey. You being a rascal. His name's Niles. He's a doll. He's about 1. Hope you get to meet him one day. Okay. Go back to your bone. So, thermal system elements. Systems in which heat flow is of interest are called thermal systems. For instance, heat generated by an engine or a server flows through several bodies. 3 modes of heat transfer: conduction, convection, and radiation. This, of course, is a dynamic process. It would require a spatial continuum. However, we are with, say, the maximum temperature of an engine, when a maximum temperature engine will reach different speeds, or the maximum density of a server farm while avoiding overheating. So those are the types of questions that we're going to be or how affect temperature response. That's mainly what in thermal system modeling. As with electrical, mechanical, and fluid systems, we can describe thermal systems as consisting of discrete, lumped parameter elements. The dynamic models that can be developed from considering these elements are the right granularity for system-level design. So, similar to fluid elements or electrical elements or mechanical elements. If you wanted to understand it at a very, very detailed level, you would need, but the level that we're concerned about from a system level design perspective, this is parameter elements for modeling thermal systems. Let a heat flow rate Q, with SI units in watts, and temperature T with SI be input to a port. There are 3 structural differences between thermal systems and the other types we've considered. So, mechanical rotational, electrical, and fluid. We're confronted with the first here, the first of the 3 differences. When we consider that heat power is typically not considered to be the product of 2 variables. Rather, the heat flow rate Q is already power. Q is in watts, so it's already power. 5 of variables that are the product of which are in heat, but we don't often deal with those quantities in the sort of measurement and intuitive world. So we'll just stick with the quantities that we understand pretty well: heat and temperature instead. A thermal element has 2 distinct locations between which its temperature drop is defined. We call it reference temperature ground. Okay, so similar to other types of systems. Work done on the system over the time interval from 0 to t is defined as the integral of the power over that time interval. Therefore, the work done on a thermal system of the heat flow is the integral of the power, also just the integral of the of Q also over time, and plus an initial condition. We now consider an element that can store energy, called an energy storage element. Oop, we can keep going down now. Isn't that sweet? An element that resists power flow. An energy storage element. Can store energy. We'll also introduce. And 2 elements that can supply power from outside a system called source elements. The second difference is that there is only one type of energy storage element in the thermal domain. So this is the second difference between all the other types of energy domains we've considered and the thermal energy domain. There's only one type of energy storage element. It's because there is only in nature a thing that is a thermal inductor. But so far, okay. When heat is stored in an object, it stores potential energy via its temperature T. Okay. This is analogous to how an electronic via its voltage. For this reason, we call elements thermal capacitors. A linear thermal capacitor with thermal capacitance C, joules per Kelvin, heat H has the constitutive equation H equals CT. Once again, time differentiating the constitutive equation gives us the elemental equation. We're going to switch sides here too, so dt will be on one side, equals. The other side you divide, and dH dt is just by Q. So there's our elemental equation. The thermal capacitance C is an extensive property, the amount of its substance. C, which is in units joules per Kelvin per kilogram, an intensive property, or one that is independent of the amount of its substance. These quantities are related for an object of mass m by the equation C equals mc. Okay, so that was thermal capacitors, and really most quantities can be modeled bodies that can hold heat in them at all capacitance. Now, when we have a body that has maybe side, then we would talk about thermal resistance. But thermal resistance can also be applied to other types of situations, not just a conductive or, in this case, insulating material. So we'll talk more about this now. So thermal resistors are defined as elements for which the heat flow rate Q through the element is a monotonic function of the type of T across it. Linear thermal resistors have constitutive equation. It turns out elemental equation, Q equals 1 over R T, where R is called the thermal resistance. Thermal resistors do not dissipate energy from the system, which is the third difference between thermal and other energy domains we've considered. The other resistive elements all dissipate energy to heat. Rather than dissipate energy, they simply impede its flow thermal system. So it doesn't have anywhere to go. It's already heat. So it doesn't really dissipate any energy from the system. It stays in the system. It just impedes the flow of heat. All three modes of heat transfer are modeled by thermal resistors, but only two of them are well approximated as linear for a significant range of temperature. So first is conduction. Heat conduction is a transfer of heat through a particle interaction. It is characterized by a thermal resistance R equals L over rho. The object is the transverse cross-sectional area, and rho is the materiality. That one I think you guys were expecting. Convection also is pretty well approximated by linear resistance. So heat convection is the transfer of heat via fluid advection, which is the bulk motion of a fluid. It is characterized by a thermal resistance R equals 1 over HA, where H is the convection heat transfer coefficient, A is the area of fluid object contact. The convection heat transfer coefficient H is highly dependent on the velocity of the fluid. Furthermore, the geometry of the objects and the fluid composition affect H. So, although it looks like, wow, convection is really easy to model in terms of a linear resistor, well, to a point, it does have this H coefficient in it, which is a really tricky parameter to approximate, and you spend a lot of heat transfer the whole course talking about H. Okay, radiation. Radiative heat transfer is electromagnetic radiation emitted from one body and another. For sure, but absolute emissivity or absorbed surfaces, the heat transfer is characterized by Q equals epsilon sigma A times this striking T1 to the fourth minus T2 to the fourth, where sigma is the Stefan-Boltzmann constant. This is a pretty radical equation. T1 to the fourth minus T2 to the fourth. Okay, the 7 Boltzmann constant I gave there. Clearly, this is linear. Linearization of this heat transfer is problematic. T between the bodies does not appear in the expression. Now, you had to actually put in, whereas up here we could use the linear equation with T in it. You can't. You have to use the absolute temperature of T1 and the absolute temperature of T2. And that causes problems for us because we want it in terms of the temperature difference. T between the bodies. For many system models, radiative heat transfer is assumed negligible. We must be cautious with this assumption, however, especially when high operating temperatures are anticipated. We would like it to be negligible, but we have to be careful because it's not always. Okay. Sources. So thermal sources include many physical processes. Almost everything generates heat, so it's really didn't make a lot of sense to start naming things. Pretty much everything generates heat. Entropy and heat being the lowest ordered form of energy and all that stuff. Remember how the universe is headed towards its eventual heat death? Yes. Happy day. Okay, so an ideal heat flow rate source is an element that provides arbitrary heat flow rate QS to a system, independent of the temperature across it, which depends on the system. An ideal temperature to heat flow rate source is an element that provides arbitrary temperature TS to a system, independent of the heat flow rate through it, which depends on the system. So it's very similar to current source. It's a sort of dual sources. Okay. Generalized element and variable types. When keeping with the definitions of System Dynamics Volume 1, temperature T is an across variable, through variable. So those are the two types of variables that we defined. Consequently, is considered an A-type energy storage element. A thermal resistor is considered a D-type dissipative element, although it does not actually dissipate energy. It does, however, resist its flow and relates its across and through variables algebraically, both signature characteristics of a D-type element. Temperature sources are then across variable sources, and heat flow rate sources are through variable sources. So all of our construction rules for linear, taking a linear graph and constructing a normal tree and then deriving a state space model from that can apply for these thermal systems where thermal capacitors are A types, thermal resistors are D types. I'm going to actually do it's fun.